Hi, welcome to my COMP4731 Research. My name is Don Hyuk Choi, Mike, also known as Mike, and I will be talking about the Mac OS and CPU scheduling algorithm, memory management, and I/O input and output. So what I found for the Mac OS was that it uses both round robin and multi-level feedback queue for scheduling for their CPU. So a basic overview of the round robin schedule. So each process gets a small unit of time called quantum, usually about 10 to 100 milliseconds long. A process is executed for the given time quantum. It is preempted and other processes executes for a given time period as well. Um, it is a simple, easy way to implement and starvation free as all processes of get a fair share of the CPU. One of the most commonly used techniques in CPU scheduling as a core. So it is preemptive as processes are assigned CPU only for a fixed slice of time at most, and it is widely used a scheduling method in traditional OS. And some advantages would be that it is fair since every process gets equal share to the CPU. New processes are added to the end of the ready queue, and processes get a chance to reschedule after a particular quantum. Some disadvantages would be that there's low throughput, there's a lot of context switching, and there's a large waiting time and response time. And now we move on to multi-level feedback queue. So it keeps analyzing the behavior of processes according to how it behaves. It changes the priority. If a process uses too much CPU time, it moves to a lower priority queue, and the other way around as well. This form of aging helps to prevent starvation for the processes. So, aging is when process priority gradually increases while waiting in the system for a long time. To optimize turnaround time, algorithms like SJF is needed, which require the running time of process to schedule them. But the running time of the process is not known in advance. So the multi-level feedback queue schedule runs a process for time quantum, and then it can change its priority. Thus, it learns from the past behavior of the processes, and then it can kind of predict its future behavior. This way, it tries to run shorter processes first, thus optimizing the turnaround time, and it also reduces the response time. And some advantages would be that it covers the disadvantages of all other scheduling, and it can also be configured to match a specific system under design. Disadvantages is that it is very complex and is hard to understand. And some facts about multi-level scheduling is that it gives preference to short jobs, gives preference to input and output bound processes, and separate processes into categories based on their need for the processor. And now we will move on to memory management. The VM stands for Virtual Memory System, which is used in Mac OS, and is a descendant of Mach VM. The design of Mac VM centers around the concept of physical memory being in a cache for virtual memory. Mac OS has a fully integrated virtual memory system that you cannot actually turn off. As memory gets full, sections of memory that are not being used are written to the disk to make room for data. The portion of the disk that stores the unused data is known as the backing store. And another thing is that when the Mac OS starts up, it divides the available RAM into two sections. It reserves for itself a zone or partition of memory known as a system, and the system partition always begins at the lowest addressable byte of memory. So in macOS, the kernel associates the virtual memory object with each region of the logical address space, and the kernel uses the VM object to track and manage the resident and non-resident pages. So there are three system-wide lists of physical memory pages. There is the active list, inactive list, and free list. The active list contains pages that are currently mapped into memory and have been recently accessed. The inactive list contains pages that are currently resident in physical memory but have not been accessed recently. These pages may contain valid data but can be removed from memory at any time. The free list contains pages of physical memory that are not associated with any address space of the VM object, and these pages are available for immediate use by any process that needs them. Paging out process. When the number of pages in the free list dips below a computed threshold, the kernel reclaims physical pages for the free list by swapping inactive pages out of memory. So a simple example would be that if a page in the active list is not recently touched, it is moved to the inactive list. And if a page in the inactive list is not recently touched, the kernel finds the page's virtual memory object. And if that virtual memory object has never been paged before, the kernel calls the initialization routine that creates and assigns a default pager object. And the virtual memory object's default pager attempts to write that page out to the backing store. And if the pager succeeds, the kernel frees the physical memory occupied by the page and moves the page from the inactive list to the free list. Paging in process. The final phase of virtual memory management, which moves pages into physical memory. A memory access fault occurs when code tries to access data in a virtual address that is not mapped to the physical memory. So, as we learned, there are two different kinds of faults. There's a soft fault, which can occur when the page of the reference address is resident in physical memory, but is currently not mapped into the address space of the process. The hard fault occurs when the page of the reference address is not in physical memory, but is swapped out to backing store, and this is what is typically known as a page fault. And Mac OS input and output. In Mac OS, the I/O kit provides a model of system hardware in an object-oriented framework. And there's three major conceptual elements of the I/O kit architecture: families, drivers, and nubs. The macOS I/O kit was written in C++. The C++ compiler is mature, and the language provides support for system programming. In addition, there was already large community of Macintosh developers with a C++ experience. And the IO kit is based on three C++ libraries. There's a kernel/IO kit, the library used for developing kernel resident device drivers. Kernel/libkern, the library containing classes useful for all development of kernel software. And IO kit, the framework used for developing device interfaces. And Mac OS IO kit features. Dynamic and automatic device configuration, plug and play. Um, Many new types of devices, including graphic acceleration and multimedia devices. A power management. The kernel's enforcement of protected memory, separate address spaces for kernel and user programs. Preemptive multitasking, symmetric multiprocessing, common abstractions shared between types of devices, and enhanced development experience. So new drivers should be easy to write. So moving on to families. Families define a collection of high-level abstractions common to all devices of a particular category. They're dynamically loadable. They're loaded when they're needed and unloaded when they're no longer needed. So families may include headers, libraries, sample code, test harnesses, and documentation. They provide the API, generic support code and at least one example driver. And families provide services for many different categories of the device. Common abstractions are defined and implemented by the family among all drivers in a family to share similar features easily. Instead, you could concentrate on device specific details that can make your driver different from other drivers. The use of families means that there is less code for you to write, and some families may be preloaded at system startup, and they are dynamically loadable. So drivers. Drivers is an IO kit object that manages the device or bus. When a driver is loaded, its required families are also loaded to provide necessary common functionality. So the request to load a driver causes all of its dependent requirements to be loaded first. After all requirements are met, the requested driver is loaded as well. So um, the families are loaded upon demand of driver, and it's not the other way around. So the families cannot um, be loaded after the driver. Occasionally, a family may already be loaded when a driver demands it. However, you should never assume this. To ensure all requirements are met, each device driver should list all of its requirements in its property list. And most drivers are in a client-provider relationship, wherein the driver must know about both the family from which it inherits and the family to which it connects to. Nubs. Nub is an IOKit object that represents a point of connection for a driver, defined as a controllable entity such as a disk or a bus. So a nub is loaded as part of the family that instantiates it. Each nub provides access to the device or service that it represents and provides services such as matching, arbitration, and power management. Each nub provides a bridge between two drivers. It is most common that a driver publishes one nub for each individual device or service that it controls. It is also possible for a driver that controls only a single device or service to act as its own nub. So in simpler terms, a nub is an IO-kit object that represents a communication channel for a device or logical service and mediates access to that device and service. So for example, a nub could represent a bus, a disk, a graphics adapter, or a keyboard, mic, mouse. And we move on to driver matching. Driver matching is an IO kit process in which a nub, after discovering a specific hardware device, it searches for a driver or drivers most suited to that device. So there's three main things to cover for driver matching. So there's class matching, which eliminates drivers of the wrong device class. And there's passive matching, which examines each remaining driver's personalities of properties specific to that device, eliminating those drivers that don't match. Active matching. The remaining driver candidates probe the device to verify that I can drive it. And thank you for watching my video.